This is a PERT problem. In PERT problems, activity times are triple time estimates. So what we will do is use the 3-time estimates to compute the average time. This is the equation that we will use for computing the average time for each activity. Let me first show you this. If the difference between the optimistic and most likely time and the difference between most likely time and the pessimistic time are the same, then the middle value is going to be, or that most likely value is going to be the uh, average duration. So for instance, in for activity 2, the times are 3, 6, and 9. So 3, 6, and 9. Each of those pairs are 3 units apart, so it's the same distance. So the duration for this activity is going to be 9, which is the center or the middle value. For activities that rule does not apply to, we must use this equation right here. I have done it for activity 4. You can see that activity 4 has these durations. Those have been used to compute an average time of 5. If the time that you compute as an average is not a whole number, is not an integer, go ahead and at least use 1 or 2 decimals, because if these are months, then the fraction of a month can make a big difference in the delivery time of the project. So activities 8 and 11 also must use that equation. Using that method, I have created all the time estimates, average time estimates, and in this one, I have actually computed the forward and the backward pass. At this point, if you want, stop the video and make sure that you can compute those times on your own. Notice that for activities 10 and 11, since both of those are finishing activities for the project, I have arrows drawn into a finish node, and I use the forward pass. The differences between the 17 and 25, and I have used 25, which then, because finish node is not really an activity, it's a point in time when the project finishes, then if I add 25 and 0, I get 25. Using that 25 to be my latest finish time, then I can work it backwards, and that gives me no slack for activity 11, but 8 units of slack for activity 10. Accordingly, we compute the critical path. Notice that the critical path is activities, or actually I can compute time for critical path, which is comprised of activities 2, 5, 8, and 11. Adding those times up for those activities, I get 6 plus 3 plus 7 plus 9, which gives me 25. So the average time to complete this project is 25, which is indicated with our forward pass calculation. We can also compute the sigma squared for the critical path, or variance. That would be the variance for each activity using the equation here, where we subtract find the range for activity time squared and divide by 36. Notice the variance for, let's say, activity 2 is, notice the times for activity 2 were 3, 6, and 9. So variance for activity 2 is 3, 6, and 9. So 9 minus 3 is 6. 6 squared is 36. So we get 36 out of 36. The same way, we compute 36 out of 36 for activity 2, 4 out of 36 for activity 5, 64 out of 36 for activity 8, and 100 out of 36 for activity 11. That summation is 5.67 weeks squared. So if I take square root of it, the sigma will be, for critical path, the sigma will be square root of 5.67, which gives me 2.38. So essentially, using central limit theorem, if that applies, then we're saying that this project on average takes 25 weeks to complete with a sigma of 2.38 weeks. So we can compute probability that project time will be less than or equal to any number, probability that project time is greater than or equal to any number, probability that project time falls between two different time estimates. We can also compute the probability of a certain service level and what our due date should be to promise such a due date so that we can finish the project by that deadline with a certain service level.